This is Computer Programming 1 from the University of Washington. I'm Martin Dickey, and I'd like to welcome you to Lecture 3 of this course. Today we'll be talking about our first really nitty-gritty detailed topic in C programming: variables, values, and types. Some of the things we'll talk about today include variables and their declarations, identifiers and reserved words, types, expressions, assignment statement, and variable initialization. As I think you can already see, a lot of new concepts, a lot of new terminology is coming up. But let's step back and look at what a computer is. As we discussed last time, the important parts of a computer you can't see. They're buried deep inside. But these two parts, the central processing unit and the main memory, are what make a computer a computer. Last time we focused on the central processing unit and the fact that programs consist of statements which the CPU executes one by one. Today we'll be focusing more on the main memory and the role it has to play in our programs. As in the last lecture, we'll also be looking at a real C program, in fact two real C programs, and this time we'll be able to study them in a great deal more detail. Memory, as we said last time, is a collection of locations. And in a language like C, we get at these memory locations using variables. Today we'll spend a lot of time talking about how we get these variables in the C program and some of the things we can do once we have them. Variables have names, which are identifiers. Identifier is just a fancy word in programming languages for a name. And variables also have types, and this concept is perhaps a little new. The type of a variable determines the kind of values that it can take and the kind of operations that can be performed with it. Some types are numbers. And there are two of these that we'll study in this course. One is called int. An int type of variable is used to hold integer numbers. These are numbers, as we're used to them, whole numbers without any fractional part. Minus 17, plus 17. Both of those are ints in C. Doubles are values that can have fractional parts, such as 3.14159. There's a third type we use in this course called character, or abbreviated char. This can contain a single symbol, such as might be displayed on a screen or typed in from the keyboard, a letter, or perhaps a number, but a number considered as the symbol, a numeral, rather than a value. So to show this difference, when I reference characters, I'll always use single quotation marks around a value. 9 with single quotation marks is the symbol or numeral 9. 9 without quotation marks is an integer value. To picture variables, we often draw diagrams that show a box. The box symbolically represents the location in the memory. And to make things clear, we label the box with the name of the variable. In this picture, I've shown three different variables. First one is named I, and its value, that's the value stored in the variable in memory, is 12. It's an integer variable, as you can see, because it has no decimal point. Gas price is another variable. Its name is gas price, and in this example it contains $1.79.9. That's more than I paid for gas on my trip to the Midwest last week. The third variable is named bang, and in this case it contains a single character. It's a punctuation mark. It's the exclamation point. Now, to use variables in a language like C, we first must declare them. That is, we have to say that we're going to use the variable, and we have to say what its type is. We always will have to do these two things in order to declare a variable in C. The pattern is a common one that we'll see many times in the C language. We first state the type, and then we state the name. So if you want to declare a location in memory, call it months, and you want it to hold integer values, you would write what we see on the first line there, int, the type, and then the name months. The semicolon is also required. One of many cases in C where a little punctuation mark makes a big difference to the compiler in determining whether your program is correct. It doesn't make any difference to us in our thought process, but we have to follow the rules that the compiler is expecting. So months, once it's declared, could hold a value like 1 or 17 or minus 32. It can't hold a value like 1.5. That's not an integer. If I want a value like 1.5, I would have to declare it as type double. So in my second declaration, I said double pi. Same pattern, which you'll see many, many times in C in different contexts. The type of something followed by its name. Once I've declared pi, I could put a value in it, like 3.14. Guessing from the name, maybe that's the value I wanted, but I could put any value I wanted into it, any numeric value. Notice the value 6.02E23. That's scientific notation. That's perfectly legal to use in C. If you're an engineer or a scientist, you might find that handy. The third set of declarations, char, we say the type, and then we give the name, first initial, and then, oops, there's no semicolon. What is that? It's a comma. The comma says we're going to declare a series of variables, one after the other, without repeating the type. So that line declares 3 separate variables, 3 named locations in memory. All of them are of type char. One is named first initial, one is called middle initial, one is called variable status. Those variables, once declared, can contain single character values like A, B, the numeral 0, exclamation point, punctuation symbols, and so forth. What they can't contain are strings like names or places. Now, computers are often called upon to process things like names. How do they do it? Well, they don't do it using single characters. In a later lecture, we'll talk about how strings can be handled in C. As we've said, variables have names. In fact, that's what a variable is. It's a named location for memory. We can't use any old name, however. The C language restricts the sorts of names we can form. This is just a rule you have to remember, whether you like it or not. It's the rule chosen by the designers of the C language, and it's also the same rule used in most common programming languages. Here's the rule. You can use letters, numerals, and the underscore character. That underscore may look strange, but it's treated like any other characters for names. Those are the only kind of symbols you can't use. You can't use other punctuation symbols. You can't use spaces, and so forth. The name can't begin with a numeral. So a name like R2D2 is perfectly legal, but 2R2D is not if it starts with a numeral 2. Maybe you'd like to have a name like that. Sorry, you can't do it in C. C identifiers can't be reserved words. I'll come back to this very shortly again. There are certain words that have a special meaning already in C. You can't reuse them. They're also case sensitive. That means it matters whether or not you use upper or lower case. A little while ago I had int month, spelled lowercase M-O-N-T-H. If I declared int capital M-O-N-T-H, that is perfectly legal, but it's a different variable. That would correspond to a different memory location. That's what we mean by being case sensitive. You can make your names about as long as you want, but you want to be reasonable about, you don't want to be too long. That's hard to type and hard to read, but if it's too short, it's also hard to understand. The name should be chosen to reflect the use of the variable in the program. It's an important and useful and easy form of documentation. Reserved words, as I've just mentioned, are identifiers that already have a fixed meaning in C, and so you can't reuse them for your own purpose. We've seen some already. Int. Okay. Int means integer. And when it means that, it has to be spelled exactly like that. You can't write it out, I-N-T-E-G-E-R. You have to spell it exactly like this. And you can't use that for any other purpose. You can't have a a variable named int. On the other hand, you can have a variable whose type is int, but its name would be something else. There are a lot of reserved words in C and in most programming languages. I'll point them out as we come to them. Now, what's happening under the hood when you declare these variables? We already have a picture of that because we know that variables are really just names for locations in memory. Now, inside the memory, the values are stored in the computer's native language, which is not numbers and characters, but it's ones and zeros. At the microscopic level, the computer circuitry are things which have two states. Often these are transistors, but they may be manufactured in other ways as well. And these two states are interpreted as a 0, meaning off, or a 1, meaning on. Everything in the computer is ultimately broken down into this code of 2 symbols. This is why we call it the binary code. It's actually pretty amazing. Everything that you can store in a computer is broken down in this fashion. Not just ints and doubles and chars, but also things like your paycheck and the MP3 sound file version of Smells Like Teen Spirit and the bootleg video copy of whatever that movie is that I better not mention so I don't get into trouble with the copyright authorities. But everything. It's really quite amazing, and it's a fascinating thing to watch as time unfolds. People learn ever and ever more clever ways of storing data using just zeros and ones. Here's a picture of one possible way the storing might be done for an int value. If we declare something as int and we say its value is 161, then on most computers it will have a binary code, as you see on the left there, 01010001. Okay. Likewise, if you say a variable is a char and has an A in it, we'll have a code. I haven't shown it there because it does differ from computer to computer. Doubles also have a code which is even more long and complicated. But the good news is, you, the programmer, almost never have to worry about what those codes are. This is one of the great things that a high-level language like C does for us. It lets us deal with what are really complicated and boringly complicated binary codes in a symbolic fashion that makes sense to us as human beings. Okay, so what have we got so far? Well, we know what memory is. We know that variables are named locations in memory. We know that those locations can hold values and that they're broken down into bits. But we haven't said how we get values into those locations. And why might we want to do that in the first place? Well, remember what memory is for. It's to hold values temporarily while the CPU is executing instructions. So for the CPU to do something, it has to have that information available in memory. So it's going to be really important in our programs that we can get values into memory, the values that we want. We'll see a number of ways of doing that. The first one, and one of the most important, is with a statement called the assignment statement. So this will be the first example of a statement that we've seen in the C programming language. It's a really important one and quite straightforward. What the assignment statement does is take a value and cause that value to be placed in a memory location. Okay? Let's look at an example. The white box shows a little fragment of code from a program. You recognize the first line now. That's a declaration of 3 variables, right? Because there's a comma separating them. Okay? Now, the next line of that block shows our new statement. Length equals sign 16 semicolon. When the CPU gets to this statement, it will take the value 16 and place it in the memory location whose name is length. So there's an activity taking place here. This is not an equation, unlike math. I'm not saying that length equals 16. I'm saying that the value of 16 is placed into length. That's an important distinction. And so to reinforce it, I'm going to try very hard when I read these statements not to say length equals 16. That would reflect an error in thinking on my part. I'm going to say instead length gets 16. Emphasize the fact that something active is happening here. There's an activity, a motion of information. The next line now you can read as what? Width gets 32. And the last line is a little more complicated looking, but the same principle is in effect here. We're putting a value into a variable. The value here is being computed before we store it. Okay? So what I'll first do is look at the right-hand side of that assignment statement. It says length times width. The CPU will get the value that's stored in length. That's one value. You'll get the value stored in width. That's another one. Take those two values and multiply them together. That gives a new result. Having done that, it will then look at the left-hand side and see where to store that value. And in this case, we're going to store it into the memory location whose name is area. Okay. You'll see many, many assignment statements as you look at programs. Some of them may look very complicated, but they all are executed in the same way. You have a left-hand side, an equal sign, and a right-hand side. And you always, without exception, start with the right-hand side. Go through the steps and figure out what the value of that is. Only then do you take that value and place it into the location specified by the left-hand side. Okay. If you remember that, it'll make understanding programs much simpler. Let me emphasize again that this equal sign is different from the equals that we're used to seeing in mathematics. This example, my age gets my age plus 1, would be really strange if I thought of it as a mathematical equation to be solved. What values of my age would make this true? Well, there aren't very many of them. It just doesn't really make any sense. But it makes perfect sense if you understand it as an activity, a sequence of operations performed by the CPU. Let's interpret it that way. Where do we start with an assignment statement? Always start with the right-hand side. So I'm going to look at my age plus 1. The CPU will find the value stored in the variable my age, take that, add 1 to it. That gives a new value. Then it will take that value and store it in the position specified by the left-hand side, which happens to be my age. And so now, what's happened? I've just got 1 year older. The assignment statement is all it took. Okay. Because we always process the right-hand side first, what's happening here is that the old value of the variable is used on the right-hand side, even though a new value might be stored as a result of the variable on the left-hand side. Okay. You don't do this in math. And this is not math. This is computer programming. And here's one of the differences. Okay, so now we know how to declare variables. And, also important, we know how to put some values into them. We know how to use the assignment statement. Okay. Now that's not quite enough to write really useful programs, but it's certainly a lot. A lot of programs consist just of this, of declarations, of assignment statements, and then a few additional statements. Okay. When the program has been written and translated and linked and put into machine language formula, the CPU will start executing with the first statement. The variables will already have been set up, and it knows where their names and locations are. So the CPU will begin executing with the first statement of the program, and then continue to execute one statement after another. Let's look at a concrete example now. This is another program. Now, the one I showed you last time, we went over pretty fast, a lot of hand waving. But this time we'll be a little more methodical about it because virtually everything in here we now can explain. The first two lines are boilerplate that I won't explain yet, but Following that, we see 3 lines that start with int. You now recognize these as declarations, and you know what's happening here. We're declaring 3 memory areas and giving them those names: rectangle, length, width, and area. Okay. What's this program doing? What problem is it solving? Well, it's already written. I didn't go through the steps with you of writing the program. But fortunately, the programmer left behind a nice comment at the top that tells us what the program is supposed to do. It's supposed to calculate and print the area of a 10 by 3 rectangle. So this is quite a special purpose program. It only does one thing. I've got the declarations there. Following that are 3 assignment statements. See those. Then there is something that says printf, and finally something that says return. The printf and return 0 also correspond to statements in C. We'll focus on the assignment statements right now to figure out how this program is operating. Now, one way to see how programs are working is to do a hand simulation. And that is to simulate the operation of the program step by step with pencil and paper, as opposed to running it on the computer. So for the program we just looked at, that you might want to have a copy of in front of you as we talk about this, we saw there were 3 variables, and we'll depict them by making a little table. We could also draw boxes if you prefer. Then we'll take the instructions, starting with those 3 assignment statements, and execute each one of them mentally, that is, using our understanding of how the instructions work, and see what effect that has on the variables. To do this, I've made a little table. You see the variables named across the top, and each row represents one step in time. Now, after the variables are declared, but before we've done any statements, we'd like to have a picture of what's in those variables. What is that value? Well, the answer is we don't know. We didn't put anything there. Does that mean the variables are empty? Well, not really. There's something there. There's some combination of zeros and ones. Well, we don't know what it is. We could call it garbage. It's unknown. It's a question mark. Okay. Now, after the first statement, if you have that program in front of you, you can refer to that. There's an assignment statement of rectangle length gets 10. After that statement is executed, then picture changes slightly. Rectangle length now has a known value, so I put that in the column there. The other 2 variables are still unknown. After the second assignment statement, rectangle length isn't changed at all, retains its value. Rectangle width now has a value. And the third statement, which had that multiplication operation, will finally put a value into rectangle area. Okay. Now, even with a long, complicated program, you can continue this strategy, and it's often extremely helpful for understanding how a complicated or even a simple program works, especially in the case where you run the program and it doesn't work as expected. Hand simulation is one way to get firm control in your mind of what is happening. You might be a little surprised that I said we don't know what's in those variables after they were declared. If you are used to programming in a language like BASIC or Fortran, you may have learned in those languages that a numeric variable is automatically initialized to 0. That would be nice if it were true in C, but it's not true. Variables of this type in C are not initialized. That means they have whatever random zeros and ones are left over from the last time they were used, perhaps by your program, perhaps by some other program. You cannot count on them having any particular value. This is a source of errors in C programs that even experienced programmers will often fall into, assuming that an initialized variable has some known value, when in fact it doesn't. It's a question mark and needs to be thought of that way until you give it a value. How can you give it a value? We've seen one way, and that is with the assignment statement. Okay. We have a special name for giving something a value the first time. We call that initialization. Okay, so here's a new terminology. Initialization means giving a variable a value for the first time. Now, if I give it a value later on, a different value, that's not an initialization. That's simply a change in value. Remember always that variables in C are not initialized. This slide is a little bit of practice on the terminology that we've introduced so far. We've talked about declarations, assignments, and initialization. And on this slide, we see some examples with clear labelings as to how that new terminology can be applied. I'm not going to go through this slide with you, but I encourage you to look at it on your own at your leisure and make sure you understand all the comments on this slide and agree with the way the terminology is used. If you can do that, then you have a solid understanding of this new terminology and the concepts behind it. Okay, well, we've seen our first program and been able to analyze it, trace it using a simulation. Let's do one more program before the lecture ends. Let's take a different problem, one that might sound a little more useful than the ones we've seen so far. Your friend from Hong Kong or China is coming to visit and calls up and says, "What's the temperature?" And you say, "Gee, I think it was about 45 this morning." Okay. They go into shock because 45 in a country where Celsius is used would be a blazing heat wave. Problem here is communication. They're using Celsius and you're using Fahrenheit. What are we going to do? Well, you're a computer expert now, so how about writing a program that can calculate the Celsius given the Fahrenheit? So there's our problem statement. We want to convert Fahrenheit temperature to Celsius. Remember back to the steps that are recommended to follow? You do the analysis and the algorithm and so forth. Well, let's do a little of that, even with this problem. The analysis might consist of looking back in a textbook or an encyclopedia or on the internet to find out what the relationship is. Okay? You might have that formula memorized, but you might not. So you need to do some analysis to find out what it is. And there's the formula. That's not meant to be a C assignment statement. That's meant to be the simple statement of the mathematical relationship between Fahrenheit and Celsius. Another thing you would do in your analysis is decide what kind of data you have. If I say the temperature is 45, that sounds like an integer, but maybe in the future I'd have a more accurate thermometer that said the temperature was 45.5 or 0.3. And certainly the result of the computation could be a fractional value. So probably doubles is what your analysis is going to lead you to use. Okay, so we've got a problem. The analysis has given the algorithm, which is to take the Fahrenheit and apply this formula to it. We're now ready to write this in C. And you know enough C to do that. Believe me, you do. You know what the boilerplate is. For now, that has to be in every program. And you know how to declare the variables. Seems like we need two of them, with two quantities. And what's more, you can now write the assignment statement that will perform the calculation. Okay, there it is. In case you're worried about the details of the punctuation and symbols used in that assignment statement, we'll come back to that in our next lecture, and I'll give you a complete set of rules for it. But there you are. There's a complete program. You could type this in, and it would get no errors. However, as you look at it, it may occur to you that even though this program will compile without errors, it's not completely useful, and perhaps not even free of bugs. Can you see what I'm thinking of? Pause for a second and think about this program from a usefulness point of view. It does the correct calculation. The variables are declared and they're the right type. But it has at least one bug that we've already talked about. In the assignment statement, what's the value of Fahrenheit when I take that right-hand side and evaluate it? What's the value? We don't know. Fahrenheit is uninitialized. I haven't put any value in there. So who knows what I'm going to get out. And besides that, it's not very useful because I have no way of saying what I want the value to be. Okay. Now I could rewrite the program to assign Fahrenheit to the temperature I want to convert, 45.5. That would be one way to solve that problem and remove the bug of having an uninitialized variable. It still is not a very useful program because it doesn't give me the answer. The answer is stored in memory, and I would need an electron microscope to get it out. Okay, this program is looking pretty shaky now. Let me give you another version of it. It has a few more statements in it. Let's compare that to the previous one. See, the parts that are in white are what we had before, but I've added some more statements. Okay. We'll come back and explain these statements in detail, but I'll give you enough now so you can understand what the program is doing. Printf is a function, that is, it's going to call on statements written elsewhere, to put the message on the screen. The message it puts is in the double quotes, enter a Fahrenheit temperature. The scanf is another function we can use, and that takes keystrokes typed by the user and puts them into the variable Fahrenheit. Okay. So with this scanf statement, we are giving Fahrenheit a value for the first time. And what's the technical term for that? That's initialization. Okay. So the scanf line is initializing the variable Fahrenheit. Now we've got a variable with a value in it. We can perform the computation with the assignment statement. Printf, take it from me, will print the message that equals and insert the value of variable Celsius in a readable format, degrees Celsius. Put that on the screen. And then the program will end. So this is a program that will be more useful than the first one, and I encourage you to try it out for yourself. Don't take my word for it. Try this program. When we run the program, it looks something like this. The top couple lines, so enter a Fahrenheit temperature, and you type something in, and it will come back with a message looking approximately like that. Okay. What's going on? Well, if you're not sure you believe this happening, you can trace the program just as we did with the previous program. Make a little table, keeps track of the variables. I have two columns, one for each variable. And then I have a line for each step within the program. So after the declaration, we see question marks there, and we know why they're there now. After the first printf, nothing has changed. After the scanf, Fahrenheit has a known value, but Celsius doesn't. After the first and only assignment statement, both variables have values. And the next printf prints something on the screen, but doesn't change the values of those variables. Okay. I'd like to go back now to the assignment statement and pick it apart a little bit more because it has some complexities hidden in it. There's our statement. Now, remember the big picture view of an assignment statement is you process everything on the right-hand side, get that value, and place that new value into the variable mentioned on the left-hand side. Let's do that. And just to make things interesting, I'm going to use a different value. Instead of 45.5, let's use 72 degrees Fahrenheit. I think it was about 72 today. So that's a very relevant example. Okay? So, two big steps always. Right-hand side, and then the assignment to the left-hand side. Within the right-hand side, we first have to go to memory, find the current value stored in the variable. Fetch that value, we say. That's a 72. Now, we look at the formula, and we're going to subtract 32 as our next step. Why? Well, we'll get into this next lecture in more detail, but the quick answer is it's because it's in parentheses. That'll make us do that first. Okay. Then we'll do times 5.0. That gives us a 200. And last we'll do the divide by 9, 22.2. Okay. It's pretty important to know the order in which these operations are done. And there's a whole set of rules for that, which we'll take up next time. But the quick answer to the order they're done is, if you use parentheses, things will be done as you wish them to do. So use parentheses if you're unsure. Once this new value has been computed of 22.2, We then do the next phase of the assignment statement, which is taking that value and storing it where? Well, the compiler has told the CPU where the variable Celsius is located. So the CPU will take that value and store it there. That will erase any value that was already there. Okay. There are often many ways to write programs. Even within a very simple program like this, there are alternate ways I could have done things. For example, I could have renamed these variables in any way I wanted to, as long as they followed the rules of C. Okay. I could have taken this assignment statement and broken it into a couple. So here's an example of doing that. Instead of one big assignment, I have two. Celsius gets Fahrenheit minus 32, and then a second one, Celsius gets Celsius times 5/9. That will lead to the same answer. And if you're uncertain about that, then I encourage you to give it a try. Do a hand trace, as we did with the previous version of the program, and see if you don't get the same answer. We've seen a lot of new terminology today. Some of it got listed here: variable, reserved word, initialization, statement, etc. Now, if you've programmed before, or maybe if you're self-taught especially, you may have written lots of programs without knowing this terminology or without ever having to use it. And it is true, you can do a lot of programming without knowing the terminology, just like you might learn to play the piano without being able to read music, or learn to speak French without being able to read and write it. Okay. But you are not going to be able to talk intelligently with other people about your program unless you know the precise terminology. So it's very important to use it. If you have a tutor or a friend or a teacher that you are trying to communicate with, and you say there's a problem with this declaration, and what you're looking at is an assignment, they're going to be completely mystified. They're not going to be able to help you. It's very important to learn the right terminology and get in the habit of using it. If you were a student in my on-campus class at UW, you'd have a further motivation for learning the terminology because, yes, it would be on the test. Please join me next time. We'll be talking about expressions, a direct continuation of this topic. I really encourage you to review this material, however, and make sure you're solid with it before you go on. And in fact, that's my advice to you for the rest of this course. Each lecture will build on the previous one, so make sure you're solid with each one and then go on to the next. Thank you, and I'll see you at the next lecture.